In section 7.1, we did a review of some of our log properties of Algebra 2, and we used those to think about the process of logarithmic differentiation. So in section 7.2, we are going to apply some similar properties to consider a couple more rules for derivatives and exponents. So let's start off going back to this idea of changing the base of a log. So in Algebra 2 and also last class, we learned or relearned that I could change the base of a log from any base to base e. You could also change it to something other than e. E is just really helpful in calculus by using this formula. So if I use that with a numeric example, let's say that I'm considering log base 2 of 8. Well, hopefully we recall from Alg 2 that that's really like thinking of like 2 to what power gives me the number 8. And so we hopefully remember that that's the number 3. But if I wanted to change log base 2 of 8 to be an expression involving the natural log, I could say that log base 2 of 8 equals the natural log of the argument, so the natural log of 8, divided by the natural log of the base we started with, ln of 2. And if you punch that in your calculator and do that division, you will see that that's also 3. So something you probably didn't learn in Algebra 2 is we could actually do the same thing with an exponential expression. It doesn't come up a lot, but that might be a helpful strategy for something we're going to do today. So recall that if I have the expression e to the power of the natural log of 5, well, since an exponential with a base of e and a log of a base of e are inverses, they undo each other, and that's the number 5. So if I have the expression 5 to the power of x, I could think of 5 as being e to the natural log of 5. And if I raise all of that, so that's just the number 5, if I raise that to the power of x, I could also restate that as e to the power of x times the natural log of 5. And if you want to go crazy with it, I think that's the way that's going to be most helpful for us. But sure, that's the same as saying e to the ln of 5x if we were just thinking about those log properties. So more generally, if I have any base a, e to the power of the natural log of a is just a. So a to the power of x becomes e to the power of the natural log of a, where a is a constant, and it's not 0, and it's positive. And I could again rewrite that as e to the power of x times the natural log of a. So again, I think this is a tool that's going to just help us understand what we're doing today. But at the end of the day, we have 3 rules that our goal will be to memorize. All right, so let's talk about, there are 2 derivative rules we're going to learn. And recall that we learned a long time ago that if I'm taking the derivative of e to the x, it's just e to the x. It's like my favorite derivative rule. However, it's not so clean when that e is not an e, so when we have a different base. So first, let's prove this to ourselves first, looking at logarithmic differentiation. So this first, on the left-hand column, let's do this with logarithmic differentiation. So we said our first step, if I'm using logarithmic differentiation, is to take the natural log of both sides of our equation. And then my second step is to apply log properties to simplify. I don't know if simplify is always the word we want, but to rewrite that right-hand side in such a way that I can take the derivative more easily. So I'm going to pull that x out and put that as a multiple of the log in front. Then once we're in that format, we said that's when we're going to want to take the derivative with respect to x on both sides of our equation there. So on the left-hand side, we kind of get this predictable outcome, 1 over y times y prime, or dy dx. I know I'm kind of alternating notation because I'm too lazy to write dy dx. And on the right-hand side, in a lot of the problems we did in class, we had to use the product rule, but a is a number, so the natural log of a is a constant. So I don't have to use the product rule. It's like if I take the derivative with respect to x of, say, like 8x, I just get 8, right? So on the right-hand side, when I take this derivative, all I get is the natural log of a, because I could think of that as the constant coefficient of x. All right, we said then to clean this up, we want to multiply both sides by y. So that's going to get rid of the 1 over y on the left-hand side. And then lastly, since I know y is a to the x, using substitution, I'm going to rewrite this as the natural log of a times a to the x. All right, so if I think about it, that wasn't too bad. And we could do that when we need this derivative, but we could also just memorize this formula. And we could check this real fast. What if we applied this rule with base e? So what if I did have y equals e to the x? My y prime would be the natural log of e times e to the x, and that's just e to the x. So that holds with what we've already learned about the derivative of e to the x. Now, there's just one other method I want you to consider if you want to flex your Alg 2 knowledge or your exponential and logarithmic knowledge, is what if we instead had changed the base of that exponential to, instead of a to the x, what if I called that e to the power of, and I'm going to use how I wrote this up here, x times the natural log of a, because we said e to the ln of a is just a, and I know I skipped a step to get to this second way of writing it. All right, so now if I use this rule, I can really bypass using logarithmic differentiation to prove this to myself. So if I take the derivative of the left-hand side, that's just our dy dx or y prime. On the right-hand side, I just need to remember the chain rule. So when I take the derivative of e to some junk, I get e to the junk times the derivative of the junk. Well, remember, again, ln of a is a constant, so the derivative of x times ln of a is just ln of a. So here's where we've got to think about that rewrite. Again, using those properties of logs, I know this is the same as e to the ln of a, all of that to the power of x, because if I have two things being multiplied as an exponent, I could write that as a power of powers like that. I still have my times ln of a out here, and e to the ln of a just becomes a. So I get a to the x times ln of a, both times that I do that. All right, so that's one of the rules that we're gonna want to memorize, but if you forget it, there are two options for how we could derive it algebraically. Okay, so now let's have some more log fun. I'm never tired of having fun with logs. I swear I have other interests besides math though. So let's say that instead I want to find the derivative of a log that has a base that's not the natural base. So recall, we learned a long time ago that if I take the derivative of the natural log of x, I just get 1 over x. So that's the rule I know, but I don't know what to do when I'm taking the derivative of a log with a different base. The first thing I'm going to do is exponentiate both sides of this equation with the base a. So when I do that, the left-hand side is a to the power of y, and the right-hand side is just x. Now wait a minute. That looks a lot like what we were just taking a derivative of up here, except the x's and y's are switched. So when I take the derivative in the next step, I have to remember that I'm really doing implicit differentiation when I take the derivative of y with respect to x. So if I'm now going to take the derivative of a to the power of y, well, it's like I could use the rule that I just learned up here. The derivative of a to the power of x was the natural log of a times a to the x. But since it's a y and not an x, I'm going to pick up a y prime. So I get the natural log of a times a to the y times y prime, again, because I'm taking the derivative of y with respect to x, and that's just the chain rule. But on the right-hand side, the derivative of x with respect to x is just 1. So now if I want to solve this for y prime, I could divide both sides of this equation by the natural log of a times a to the power of y. And so when I rewrite that, I now have y prime equals 1 over the natural log of a times a to the power of y. And remember, a to the power of y is equal to x. Like I got that relationship by exponentiating this equation. So that's the same as saying y prime equals 1 over ln of a, which is, again, that's a constant, times x. And you'll see that written a couple different ways, but that is how we do that. Now, let's say that we forget this, or that seems hard. That did seem a little harder than the last one. We could also just change the base of the log in the first place. So if I apply the change of base formula, I know that log base a of x is equal to the natural log of the argument over the natural log of my original base. So ln of x over ln of a. So I could just instead take the derivative of ln of x over ln of a. And if you're thinking to yourself, oh no, we got to use the quotient rule, we really don't, because remember, ln of a is a constant. I might also rewrite this as just like 1 over ln of a times ln of x. Well, 1 over ln of a is still a constant. So now when I take the derivative, my constant comes along for the ride. It's just a constant multiplier. And then when I get to the ln of x part, again, I don't need the product or the quotient rule here because 1 over ln of a is a constant. I get just the derivative of ln of x, which is 1 over x. And that's the same thing as I got on the other side. So lots of ways we could write that. I think in our text, I'm going to cheat and look. In our text, the x is written first. It doesn't really matter. We know multiplication is commutative. So I could write that as 1 over x times ln of a, or ln of a times x. But potato, potato, that is the derivative rule for that one. So sometimes using the change of base method is easier, or I personally find it much easier. Okay, so there's one more rule that we're going to learn. We're going to learn how to integrate when we have an exponential that has a base that is a and not e. So just a quick reminder, we have not learned any integration rules with logs, but what we do know is that if I integrate e to the x dx, I get e to the x plus c. All right, so what we could do here is, again, a change of a base, and then I think we're going to need a little u sub for this. All right, so just like before, let's rewrite a to the power of x as e to the power of ln of a times x. I'm going to put the x in front. All right, so when I integrate this, I'm going to rewrite this as e to the power of x times the natural log of a. And again, natural log of a, it's a constant. It depends what number we choose for a, but a is a constant, so ln of a is also a constant. So I'm going to do a u sub here. So let's let u be x times the natural log of a, which means our du would just be the natural log of a dx. So that means I need to create a constant multiplier. So, let me change colors. So in my integrand, I've got x times ln of a. I'm going to create that constant of ln of a that I need for my u sub, but out here I need to undo my constant. So I got a 1 over ln of a, just like we do when that's like the number 2 or something. All right, so now if we u sub this stays out here. The ln of a gets absorbed in my du, so I get e to the u du. And I know that rule, So 1 over ln of a times e to the u plus c. And if I go back and do my substitution, that is e to the x times ln of a plus c. And again, when I get to that spot where I have e to the x times ln of a, that's like a really complicated log way of just writing a to the x. So that becomes 1 over ln of a times a to the x. So sometimes we'll just put a to the x on top plus c, our constant of integration. All right, so here's the big takeaway. If we're, let's say, taking an AP exam like second week of May, Monday, 8 a.m., I don't want to have to derive any of those rules. So these are all the rules on the left, and this is also in our spiral, probably not this font. These are all the rules on the left that we already know. Like, we don't need to do anything here. We know these rules already. But on the right is just the more general form. So all those rules that we learned back in Unit 3, or the integration rule in Unit 6, that was really specific for when we have an exponential or a log base e. So I would just encourage you to memorize these, and they're really similar. It's just a matter of thinking, like, are we multiplying by the natural log of a, or are we dividing by the natural log of a?